Hello, and welcome to another ME372 lecture. I would like to start today's lecture by talking about one of my heroes. And this picture here is of one of my heroes, Dr. Librescu. And Dr. Librescu was born in Romania during World War II. And he had a really rough life as a young kid. It was really challenging for him to get an education. But with diligence and hard work, he obtained a PhD and became a professor. And he was a professor at Virginia Tech, where I received my PhD. And I actually had a class from Dr. Librescu, and he was just amazing. Here is a page of one of his notes from his note packet. So this is just a typical page. Everything was handwritten. This is page 25, and you can see that in the development of these equations, we're on equation number 58. Here's 60 and 61. And we were supposed to read through these notes and somehow understand this material. But the way in which Dr. Librescu taught, it was such that you did learn the material. And it was one of my favorite classes that I ever took as a student, even given these difficult pages to try and understand. It was an advanced class in stress analysis of plates and shells. In 2007, there was a gunman that went to Virginia Tech, and he went into the engineering building. He chained the doors shut and then went around to classrooms and started shooting people. Dr. Librescu was teaching a class at the time. He was actually teaching the very class that I had from him, and in the very classroom that I had it from him. And when the gunshots started getting closer, Dr. Librescu ran to the door and slammed the door and held the door shut while his students were jumping out of the second-story window to the ground. The gunman tried to break into the room, and in doing so, as Dr. Librescu was holding the door shut, he was shot to death by the gunman. There's no doubt in my mind that that single act has landed Dr. Librescu to the exact place that I want to end up someday. I have the highest respect for Dr. Librescu. I love the man. I love what he stood for, and I love how he lived his life and what he did at the end of his life. I would strongly encourage you to read through this little history that was published about Dr. Librescu. And I would encourage you to try to be a Dr. Librescu. Try to be like him, follow his ideals, and learn from his examples. He's one of my great heroes, and I will never forget what he did for me as a student in the many times I was in his office for office hours, and how he taught me the mechanics of materials and stress analysis, and then what he did at the end of his life to try and protect his students with his life. Before we get into combined loadings, we need to define what we call a stress element, because we will use stress elements throughout the rest of the semester. And so it's important that you understand what we mean by the term stress element. So stress elements are a convenient way to visualize the stresses at a point in a body. A stress element is drawn with finite dimensions, but represents an infinitesimal point at a specific location. In general, stress elements are three-dimensional and are drawn as 3D cubes. However, in many machine design applications, and in most of those that we use in this class, because of the loading in geometry, the 3D stress state is reduced to a 2D stress state, and a 2D square can be used to illustrate the stresses. So for us, most of our stress elements will be in 2 dimensions. When using 2D stress elements, the stress element typically references a point on the surface of the machine component. Since the stress element represents an infinitesimal point on the structure, the stresses must be equal in magnitude and opposite in direction on opposing faces. So tension stress is illustrated by arrows pointing away from the element, and compression stress is represented with arrows pointing into the element. And shear stress is shown to act along the sides of the element. The figure below illustrates three stress states, or three stress elements, on a cantilever beam. Element A represents the infinitesimal point at the top center of the beam, indicated by the shaded region. So even though this element A is shown as a finite-sized element, it represents a single point, a single dot, right at the very top of the cantilever beam. Element B here, shown as a finite-sized element, represents the point exactly at the 90 degrees angle from element A, right at the end of the beam. And element C here is just at some arbitrary location on the surface of the cantilever beam. So the important thing to remember is that stress elements in 2D represent an infinitesimal point, and we draw them with a finite size. In practice, stress elements are placed at locations of maximum stress. These locations are typically found using shear moment diagrams and experimental testing. When a cut is made in the member, the stress elements are placed so that one edge of the stress element is right at the cut. This edge is referred to as the cut edge and is used to determine the directions of the stresses that act on the stress element. So assuming a cut at the wall in the cantilever beam shown below, the cut edge of the elements A and B would be as shown in red in the figure below. So here's a top view of my cantilever beam on the previous page. Looking straight down on the beam, we would see element A, and the cut edge of element A would be shown by this red line. The cut edge for element B would be going right into the page. Here we're looking at a side view of the cantilever beam, and we see the cut edge of element B. So it's important when you draw a stress element to always represent what we call the cut edge. And the cut edge is where you make the cut. We're now ready to start one of the most important example problems of the semester. What we have here is a circular cantilever beam fixed back here at the wall. We're applying a transverse load of 550 newtons and an axial load pulling on it of 8,000 newtons. We're also applying a torque going around in this direction of 30 newton meters. The length of the beam is 100 millimeters, and the diameter of the beam is 20 millimeters. We've defined an x-axis coming along the length of the beam, a vertical y-axis, and a right-handed coordinate system then, putting our fingers in the direction of x, wrapping them into y would give us a positive z in this direction here. And what we have been asked to do is determine the stresses that act at the top point and this side point. So what we do is we go put a stress element up here on the top and a stress element that is 90 degrees away from that right here at the side. And what we've been asked to do is compute the stresses then that act on stress elements A and B and draw them on those stress elements. So to do this, the first thing we need to do is define the coordinate system. Then we need to determine the location, and the location here is at the wall, has been determined for us. Now what we do is we make a cut at the beam wall interface and compute the reaction loads. So if I turn this beam and look at it straight into the side, my x-axis is coming along here and my y-axis is going vertical, and I'm looking straight down the z-axis. Here's my 8,000 axial load. Here's my 550 Newton transverse load. And here's my 30 Newton meter torque. And what I need to do then is I've made a cut here at the wall. I need to find the reactions due to these applied loads. And we find reactions by summing forces and moments. So coming up here, I sum forces in the x direction, and that has to equal 0. And in the x direction on this member, I'm going to have a reaction force pulling on the beam this way, and the applied load pulling on the beam this way. So I have minus Rx, because it's going in the negative x direction, plus 8,000 equals 0. So my reaction force in the x direction is equal to 8,000 pulling in this direction. I do summation of forces in y, and in y I have the same thing. I have a reaction force back here at the wall in the y direction called Ry, and then I have a 550 Newton load in the negative y direction equals 0. Solving for Ry, I get 550. Summation of forces in the z is equal to 0 is easy to apply because there are no z forces. So this step here can be done quite quickly by just simply looking at this structure. Now here's where you want to be careful, and I would encourage you to follow the process that I'm going to show you to do summation of moments. We write one equation for the summation of moments. So here I come and write the summation of the moments at the cut. So summation of moments at this cut face is equal to 0. And what I have here is I have the moment at the cut. So whatever moment exists here is represented by m cut. Plus, now I come and look at the applied loads. And I have this 30 Newton meter torque applied, and it's in the plus I direction. So we're going to use the unit vectors I, j, and k. And the unit vector I is in the x direction, the unit vector j is in the positive y direction, and the unit vector z, or the unit vector k, is in the z direction. So I, j, and k are the unit vectors in the x, y, and z directions. So this 30 Newton meter torque is in the I direction. And what I do is I put my thumb in the direction of the torque. So I put my thumb in the x-axis, and then my fingers wrap around in the positive direction. So this is a positive 30I. Then I just simply write R cross F. And this R cross F represents the moment generated by whatever moment is generated by these forces here. And I don't look at the detail of what's being generated there. All I look at is that there are forces at that point. and I simply write R cross F. Now, after I've written this expression here, I come down and I can, in detail, look at what R cross F is. And I write this matrix, I write I, J, K across the top as the unit vectors, and then I write down R. And R is how I get from the point of interest to the particular applied load. So in this case, to get from the cut face here out to the applied load, in the I or X direction, I go 100 millimeters or 0.1 meters. I don't go anything in J, and I don't go anything in Z. So this R is given again by how I get from the cut face to the applied load. And in this case, I go 100 millimeters in I, nothing in J, and nothing in K. And now I write down on the third line all the forces that exist at that point. And I have the 8,000 in the I direction. I have a minus 550 in the J direction, and then I have a 0 or no forces in the Z direction or the K direction. And now I evaluate this cross product. The way I evaluate this is a little bit confusing, so if you have your own way to evaluate a cross product, that's just fine. You don't need to follow my way here. But I am going to encourage you strongly to follow my way of writing one moment equation, writing it out like this, and then going and getting the details like this. I'll show you how I solve my cross product, and if you want to use my way, that's fine. What I do first is take the product of these three components along the diagonal, and I get this 0. Then I take the product of the J, the 0, and wrap around to the 8,000. And I take those three components and I get another 0. And then I take the K, wrap around, multiply it by the 550 and the 0.1 and get minus 55 in the K. So you take this diagonal plus these three terms plus these three terms. And then you go minus the entire quantity, and now you go up in the opposite direction. So we're going to start at the 8,000 and take the 8,000, the 0, and the K and get a 0. And then I take the minus 550, this 0, and the I, and I get another 0. And then I take this 0 times the J times the 0.1, and I get another 0. The nice thing about writing in the zeros is it's very easy for me to come back and check my math in determining this cross product. And from the cross product, I realized that my moment caused by the forces out here on this point is simply minus 55 in the K direction. So to get my reaction moment, I know that it's a minus 55 in the K, and so I come here and put my fingers in the minus K direction and get this moment coming out of the plane like this shown here. You'll note that this is shown as a plus 55 Newton meters, and that's because we need to take this minus 55 K, plug it back into my equation here in my m-cut equation, and then I need to solve for m-cut by hauling these terms to the other side of the expression. And when I do that, I get a minus 30i, so this is in the minus I direction, and a plus 55 in the K, so this is in the plus direction. So we went through this pretty methodically, but I hope you will follow that process in computing the reactions in your combined loading problems. Now what I do is just look at the cut end, and I can forget about the rest of the beam. And so I have my 550 coming up in this direction. I have 8,000 pulling in this direction. I have my 55 Newton meters in this direction and my 30 Newton meters in this direction. Now I want to determine the stresses on each stress element. To begin with, it might help you to write down all of your options. And my options are sigma equals F over A, sigma equals MC over I, tau is equal to VQ over IT, and tau is equal to TC over J. You'll note that I have not written as an option tau is equal to V over A. And that's because back here in my structure, I didn't have any point forces right along the wall. So I don't have any direct shear in this problem due to a shear force. So I come down here now and I start usually with my forces and I say, okay, what does this 8,000 Newton force do to me? And I look over at my stress options. And I know that this 8,000 is perpendicular to this cut face. So between this cut face that's going vertical here and 8,000, it's a normal. There's 90 degrees there. So it's pulling on that cut face of element A. As I draw element A, here's the same red line here that is shown as this dot here. And this 8,000 is pulling on that red line in this direction. It's pulling on it like that. So when I look at my stresses, that is this F over A, where F is the normal stress and A is the cross-sectional area. So sigma x here, I have this F over A term. Now I look at my next stress, or my next load, and my next load is this 550 Newton load pushing up in this direction. And when I look at this, I ask myself, is this an F? And it's not, because it's not perpendicular to the cut edge. Is it a moment? No. This is a force, not a moment. So it can't be MC over I. VQ over IT, is it a shear force? And it is trying to shear that off of there. But the shear force, if I draw my stress profile here, would be parabolic, largest here at the center and zero at these edges. And so with the force pushing up through the element, if the force punches through element A, the Q in VQ over IT is equal to 0. And so this 550 newtons does not do anything to the stresses at element A. Now I look at my moments. And if we look at this torque first, we know that the torque's not an F, the torque's not an M, and the difference being that the torque is twisting, where an M would be bending. The torque is not a V, so the only option is TC over J. And this torque of 30 Newton meters indeed causes a TC over J. And if I put my thumb in this minus X direction and wrap my fingers would be going up around element A in this direction shown here by this arrow. And once I've drawn one of those arrows, I can draw the rest of them. And so I know that I have tau is equal to TC over J. The torque is 30, and I can put in the geometric terms and compute the stress. The last load that I need to consider is this bending moment. And this 55 Newton meter bending moment is trying to bend this beam around like this. If I put my thumb in the positive Z direction and wrap my fingers, it's trying to bend the beam up like that. And so when I look at that stress, it's not an F, it is an M. And so I have a bending moment there. And if I think about how the moment vector would be drawn, the arrows would be coming out of element A and wrapping around in to the bottom side of my structure. And so it would be coming out of A, my fingers would be coming out of A and around into the bottom, causing a moment about this direction. And doing that puts me in the arrow pulling out of A, puts A in tension. So I have an MC over I here that will add to the P over A that we already determined. So those are the stresses that act on element A. Now for element B, we do the same process. We'll look at each one of these forces and moments and see how it affects the cut edge of the element. We have the 8,000 newtons pulling on it in a normal direction. So we'll have the same normal stress, sigma x is P over A and the 8,000. Then I look at what the 550 does. And this 550 is sliding right along the cut edge of element B. It's parallel with that red line on element B, following it straight up along that edge. And when that's the case, Q is maximum. And so we have tau is equal to VQ over IT. And for a circular cross section, that becomes 4/3 V over A. So down here, I know that this arrow is going straight up along this cut edge. And so that's one of these two arrows here going straight up along the cut edge. And then I can draw in the rest of the arrows. And this is the 4/3 V over A. I now ask myself what the 30 Newton meter torque here does. And again, it's going to do the same thing here that it did on element A. It's going to be a TC over J, and here's the TC over J term. Now I ask myself what this 55 Newton meter bending moment does. And if we look at this and we wrap our fingers around in the direction of this moment, we see that element B is right in the middle. So B is at the neutral axis for this 55 Newton meter moment. And so there is no bending moment on element B, and so this 55 Newton meter moment does not cause any stress on element B. So I hope you can follow this through and follow this example. This page here shows us how we treat reaction forces on a machine member in terms of putting the reaction forces on a stress element. So here I have reaction forces F1, F2, and F3. And what I want to do is determine the stresses on element A here. And element A is on the front of the shaft. The cut edge is shown here by the red line. So if I look at F1, I see that F1 is parallel to the red line. It parallels the red line, and so it induces VQ over IT. And for circular cross sections, this is 4/3 V over A. And we know that since the force is going this way on the cut edge, that it goes that way on the cut edge over here. And so this arrow right here, 4/3 V over A, is given by this F1 and how it acts on element A. If we look at F2 now, F2 is going right into element A. It's punching right through the element. So it doesn't do anything to the structure because Q would be 0. It's on the outer edges, and it's on the outer edges of this cross section when looking at it in the Z or the F2 direction. F3 is going vertical, and F3 we can see is perpendicular to this cut edge. It's normal to this red line, and so it creates a P over A type of stress. So these three forces here induce these stresses here. This next slide shows how reaction moments are treated. And here we have an M1 that is positive about the x-axis. We have an M2 that is about the z-axis, and we have an M3 that is about the y-axis. If we look at this M1, we can see that if I put my thumb in the direction of X, my fingers would be coming out of the bottom of element A and up into the back of the cylinder. And this will put element A in tension with a bending stress. And so this tension over here is M1C over I, where that's the tensile stress created by this reaction moment here. M2 here is trying to twist this beam around in this direction. M2 would put this side over here in compression and this side over here in tension, and so A is right in the middle. A is at the neutral axis. So M2 doesn't do anything to the stresses at element A. M3 is not a bending moment, it's a torque. It's trying to twist element A. It's trying to twist the shaft, and so it's a TC over J. And this moment is coming around this direction, and so I need to make sure that I take this moment to the cut face. Don't slide this down to the top face and put the arrow going in the opposite direction here. You need to slide the reactions to the cut face. So sliding M3 down to the bottom creates this shear stress, TC over J, where TC over J is given by M3C over J. So hopefully this review of reaction forces and reaction moments helps you draw the stresses correctly on the stress element.